All right, good morning. My name is Josh Mormon. I'm with Perspective Labs, and I'm going to present some of the work that we've done under the DARPA Labs program. And so our project is called CASPER, and it addresses the problem of security monitoring using the unintended emissions of devices. So we'll get started. So we want to cover what are these unintended radiated emissions from processors and devices. We'll go over our system overview, how we're using GNU Radio to collect and process the data, a little bit about our machine learning backend. I'll do a video demo of our real-time streaming system, and then we want to dig a little bit deeper into the array processing because that probably has a little bit more general interest in this community, and then finish with a summary. So to get started, who is Perspective Labs? To get to Ben's question from the other day, same research group. We've been through a lot of iterations lately. You might know us previously as Vencore Labs, Applied Communication Sciences, Telcordia, all the way back to Bell Labs. Same group doing the same things. They just keep changing our name. So background. So why are we looking at this type of device security? Why are we looking at monitoring devices? Well, as everyone's well aware, IoT devices are very susceptible to they're very susceptible to all kinds of threats. And so you see in the headlines all the time about the power grid has been hacked, voting machines are hacked, smart homes. All these devices are susceptible, and so we need something beyond the traditional approaches of how can you detect whether a device has been compromised. So that is what the DARPA Labs program is trying to address. And so how can we detect this without actually running security code on the processor itself? How can we do this at a distance? So there's a well-known phenomena, and there are different flavors of it, but side channel attacks. So in particular, say cryptographic processors, researchers have been able to pull off the RSA keys by monitoring the emissions. This particular example here, they were able to pull off the RSA keys by listening to the acoustic emanations of the devices. But there's also well-known electromagnetic vulnerabilities in this area by monitoring the power consumption. You can monitor some kind of pulse signal going up and down and extract the information that's happening somewhere in the processing chain of the chip. So we want to use this to our benefit. We want to use this leaked information. And that's where the DARPA Labs program comes into play. So essentially, the goal of the DARPA Labs program is to track the program state of a processor of some either IoT device, industrial computer, something where the processing is doing the same thing over and over that we should be able to track. And we want to output the monitoring state of this device, whether it's been compromised or it's doing what it should be doing. So we've trained this thing knowing in advance what it's supposed to do, or we've learned what it's supposed to do, and then we can detect the anomaly that it's gone off the rails. It's doing something we've never seen before. And so we want to identify these signals. We want to map it to the firmware, and then there's some lofty verbiage in here about other techniques that we want to explore in this program. So how does CASPER address this? So first, by characterizing the devices, we want to understand the firmware that's running on these devices. So we might not always have access to the firmware, but when we do, we can deconstruct the firmware using lots of tools, both custom and off the shelf, and understand the control flow structure. What should this program be doing in its regular mode? And we want to be able to map these to the unintended emissions. So if we know what the program's doing, we can create these micro benchmarks and learn if we run this little bit of code in the emission space, what we are able to detect, it looks like this. This is what we see. And then we move on into the signal processing area. So how do we generate features that are going to characterize these emissions that we're seeing over the air? And there's a multimodal aspect to this, too. We don't want to just look at the RF. We also want to look at the at the power modality, perhaps the acoustic modality as well, and take all that information together, provide features to the machine learning engine. Machine learning engine, we might not necessarily have a good labeled set of data, so we want to use some auto-labeling mechanisms, use an unsupervised approach to build a model of what we see on the fly, and then be able to detect anomalies. And then our anomaly detection system, which uses three main detectors, one based on n-grams, another based on the NFA, which is the control flow graph, how the program is running normally, and then some statistical labeling. We see it do this some percentage of the time, this. When you see those distributions change, flag an anomaly. So by training on what we see in the normal state and then monitoring, then we can flag these anomalies. So we're heavily using GNU Radio as our streaming framework, both for the RF modality and then using the USERPs with the baseband front end to capture the power modality. So in the RF modality, we can take a USERP with an antenna, and I'll show a demo in just a second. We can detect very clearly, in a very simple case, you can see very clearly that the processor is emanating what we would expect from the program. And we can also use a magnetic near-field probe to zoom right into the piece of the board that we want to observe. So let's take a quick look at that, at the risk of messing this up. Let's see. So I'll run a quick flow graph here. So what I have here, I have an Arduino Uno. So I'm sure most of you are familiar with this. It's got a big, fat, but simple processor running at 16 megahertz. And I've got a very simple program, 4 states in the program. And each of these states, it's just a loop of different number of simple instructions. So about as simple as you can get. So it's already loaded on here, but now let's take a look at GNU Radio. Very simple flow graph, a USERP, time averaged FFTs, normalization, so just subtracting out the mean and dividing by the standard deviation, and then we're going to plot this. So I take my mag probe, you don't see anything when I'm not near the chip, and then I can go right onto this chip, and you can see my 4 states very clearly in the spectrum. So this processor, and we've elongated these states to make it very clear, but it does 1, 2, 3, 4, 1, 2, 3, 4. And so you can imagine if there's more complex programs going on, the spectral signatures are going to get more complex as well. So that's a big part of the research there, is coming up with what are the features to characterize these states over time. So you can probe anything. You can probe the laptop. Here's the touchpad. There's the signal. There's the line into the monitor. So just to give you an idea that everything has these unintended emissions coming out all over the place. So I'll go back into the presentation. All right, so what's causing these emanations? If you look at the Uno, so when the processor is running its instructions, it causes some shift in the voltage, and that's what's going to radiate and allow us to pick these up. So one thing that causes very noticeable emanations is loops in the code. So you can imagine if you're doing the same thing over and over, you're going to get some multiple of the clock frequency showing up in the spectrum. And that's what we see. If we put some number of instructions in the loop, we see a different spacing of the spikes in the spectrum. And if you put a different number, you see a different number of spikes in the spectrum. So signal features, how can we characterize this? Well, as you could see on the waterfall plot, it's very well characterized by the time averaged FFTs. But there's a lot of different signal processing techniques that we've looked into. Depending on the target program and the device, these have different results once we try to classify them in the machine learning. So one of the first steps, if we go back to our processor emission model, we see that because we're observing harmonics of the clock frequency, we're observing these emanations happen all across the spectrum. So this particular device is a 16 megahertz clock, and we see these big spikes every 16 megahertz with other spikes in between each of those. So if we want to observe this over RF, we've got to find the right spot to tune the radio. The RF spectrum is very crowded, and so we need to find the place where we can actually observe these at a distance without being overwhelmed by other environmental signals. So as part of this, we developed an automated band scan. So yeah, what is the best spot to tune the radio, and then how do we know? How do we analyze our band scan to know that we found the best spot? So one of the steps in getting to that ground truth was to develop a ground truth setup where we use the device under test, we use the GPIO out of that device, and then with a signal generator RF switch and a synchronized radio, we're able to collect a pulse signal from the GPIO, and then we can detect the emanations in between those pulses and then classify it. So now we have labeled ground truth of the emanations of the device. So just a simple setup, this wouldn't work in the real world for doing a band scan, but to understand each device, we can characterize it in this way. And so what we can do is calculate some sort of score based on the fidelity of the measurements we were able to get here and the accuracy of the classification. And so we found that for this particular device, which is a Raspberry Pi with the antenna 4 inches away, we were able to get very good classification, here at about 700 megahertz and over here about 1600 megahertz. And so now, how can we do this without having an instrumented setup? Just taking an antenna, setting it up next to the device. How can we then scan the band and figure out, if I want to characterize this device, where do I need to tune the radio? And so if we take measurements like that, just looking at the power spectral density, we can see that we get very big spikes in places where it's not necessarily a good place to tune the radio. Those weren't the places where we were getting good classification metrics. So we've also looked into a kurtosis-based metric. Kurtosis is a measure of non-Gaussianity. So if you have signals that are turning on and off, that should make the kurtosis metric on that frequency subband spike up very high. So that might be something that we're looking for. And so, using a kurtosis-based metric, we're able to get to some of these other frequency bands that we weren't able to get to by looking at just the power spectral density alone. So just another angle to look at the automated band scan, another metric to evaluate. So our machine learning backend, I mentioned before we're using an unsupervised approach because we want to take the features that are generated from our signal processing chain and we want to evaluate them and characterize the program, not necessarily knowing the labels in advance. And so we're using some clustering-based techniques, and I believe there's a paper coming that discusses this in more detail. So we've developed this hierarchical model. So by taking bigger clusters, zooming in, finding smaller clusters, we can find a larger number of states in the program. And then the output of the machine learning, it's a sequence of states. And so we can build a temporal model of how the states are changing over time without actually having any labeling data to begin with. So putting this all together, we're using GNU Radio as our streaming framework. We have GNU Radio with our signal processing blocks. We're publishing over ZMQ to our machine learning blocks, which are just Python, not using GNU Radio yet. And on to the anomaly detection, flag up the alerts. So I just want to show a quick demo of this. running. It's a video, and I'll explain it as we're running it. So let me pause it. Okay. So if you can see this, I know the text is a little small here. We have a simple program with two states. There's two loops, and the whole system has been trained to characterize this particular program. So it does this, then this, then this, and this over and over. And we can also see on the output here that our anomaly detection says, no, what you're running is okay. It's the same as what we've trained on. And this is just a waterfall plot, so you can ignore it. So we're running our system with an antenna placed near the device. And let me play this video, see if you get a visual idea of what's going on. So in some PCA space, we can see that there's two unique things going on, state 1, state 2. Now we're going to add a third state here, load it onto the device. And so during the loader, it kind of goes wacky. But now we see a third state. The anomaly detector says, hey, I haven't seen this before. This is new. It flags that now we're seeing unknown code. And it would raise an alert to the repository. And now we're going to load it back to the original state. It goes back to 2 states. So a very simple example, just to see how, putting all the pieces together, we can load unknown code on a device and then flag that, yeah, something different has happened. All right. So one of the key metrics for this program is standoff distance. So, it's all well and good that I can detect, if I can put a sensor right up next to a device and detect what's going on. But, in some sort of industrial environment or, some other device we might not have direct access to, that might not be that useful. So what we want to do is we want to extend the standoff range of our measurement capability. And array processing is one technique to do that by using multiple antennas, which I'm sure many of you are familiar with array processing. But why are we doing this? Well, we want to extend the range. So you can imagine if you have 8 signals, if you have 8 antennas, and you're able to coherently combine those, you should be able to get a 9 dB gain if you're able to do that well. But we want to do better than that. It's a very noisy environment. We want to be able to null the interferer. So not only just cancel noise by coherently combining, we also want to nullify interferers. And so we want to extend our range even beyond that 9 dB theoretical just from coherent combining. So the goal here, we want to find a weight vector that's going to enhance our signal of interest and that's going to bring the noise down and nullify interferers. So this is the problem. This is what we want to do, very generally. So why is this a difficult problem for this particular application? Well, it's an unknown signal. So whatever device we're trying to monitor, we don't necessarily know what the emanations are going to be. We might not have characterized it. It might be a commercial device. We don't have the code, access to the code. So if you're able to build an expensive calibrated array, you can directionally steer that towards your device. But we also want to do this with off-the-shelf hardware in a very cost-effective way. So that's kind of out of the question as well. And also indoor multipath complicates that quite a bit. So we don't know where things are coming from. We don't know where our signal necessarily is coming from in the space of the uncalibrated array. And we also don't know where our interferers are coming from. So the biggest issue is that the emanations from these devices don't have a clear training sequence. It's not like a typical comm system like LTE beamforming, where we have these pilot symbols that we can do the maximum likelihood equation and find the direction to beam steer towards. So we need some sort of a blind technique. Well, there's one characteristic that we've seen in these devices is that at particular frequencies, no matter what the code is running, we see it switch on and off. There's an on and off switching characteristic that we want to take advantage of. And that's where adaptive event processing as a technique to calculate these weights comes in. So adaptive event processing is a technique developed by MIT Lincoln Labs. And essentially, it detects change. So I'll hand wave a little bit over the math here. But if we calculate the covariance matrix of the current window in time, so we have some number of observations at the current time, and then we look back some previous window, and what we can do is by calculating the eigenvectors in that space, we can find the eigenspace in which things were changing. So that's what AEP does. It finds the direction in which things were changing, and we'll beam steer in that direction. So we've set this up in our lab back in New Jersey, and you see our beautifully constructed array here. And what we've got here is we have an array of these Vivaldi slot antennas. And so these are polarized antennas, but what we've also noticed is that the emanations from devices are polarized as well. So if we're able to cover some range of polarizations, we might catch the signal with some antennas, not catch it with other antennas. And we've used two X310s and externally shared the LOs. You can see this, this rat's nest of wiring back here. And so this is a synchronized phase coherent 8-channel system. And from some distance, we've been able to detect from a particular commercial device, we've been able to detect our signal of interest. So I'll show you some results on the next slide here. So we've got a commercial device that it goes and it runs some code once every second. So this is the cleaned up signal here after it's been AEP processed. So it goes every once per second and runs some code, and we see very loud emanations. Now with a single element, you can barely make this out. There's a few dB of that signal of interest on a particular subcarrier. So we see that poking up here. On other elements, you don't see it at all. So by combining through the adaptive event processing, by combining all the elements together, we're able to take the SNR from, in the best case, 6, 7 dB here, up to 22, 23 dB on this particular signal feature. So you can see all of the environmental noise. I think this was, in the 500 megahertz band, that we're able to knock all this down and get what we wanted out of the signal. So just to summarize, we've been able to use a combination of technologies, put it together to distinguish known, unknown code. And GNU Radio is a big part of this. So we're very appreciative of the community and the framework as part of this system. ZMQ, I think the other parts of the team that weren't as familiar with GNU Radio, we're very thankful for the ZMQ aspects of it because it allowed us to pass the data from GNU Radio to other software entities that were not running in GNU Radio. So they were very appreciative of that. We've developed also some efficient techniques to run at real-time speeds and done all of this on relatively commodity hardware. So going forward, what do we want to do? Of course, we want more robust feature extraction. The machine learning backend is only as good as the features it's provided. So we want to keep doing research in that area. We want to dig more into the power modality. The ideal goal would be, can we put a clamp on the power cord and get the same type of data we're able to get over the air just by seeing how the power changes, the power draw from a particular device. And then also with the real-time AEP, or with the AEP processing, you see these MATLAB plots here. So we've proved out the algorithms, and we're in the process of moving those into GNU Radio blocks to run in real time and integrate into our streaming system. So that's all I had.
Thank you very much, Josh.
Yeah.
All right, we have time for questions. While we're taking questions, it'd be great, Trip, if you could switch out laptops. Bill, if you could go get mic'd. And so over there first to Raphael, and then we'll go Sheesh.
It's a really good talk. Are you going to open source any of this? And are there any implementations of AEP that are currently open source?
Very good question. So I expected this question. So this is a government-funded project, and so it's been encouraged that we open source things. There's a process to get there. Oh yeah, sorry about that. So there's a process to get there to be able to open source. So we'll have to navigate that process. But the hope is in the future we will be able to open source pieces of this.
And how do you, two devices co-located, how do you distinguish those? So right now you're just assuming isolated device. If you had a whole factory of little devices, they're going to look very similar, right?
Yeah, so we're just starting to get into the multi-device aspects of this. So I don't have a clear answer for you on that. If we're able, through the AEP processing, if we see changes in two different spaces, so I mentioned that, we're pulling out the eigenvectors where we see things, change. You should be able to see two distinct large eigenvalues in that space. So that would be one method with the array will get you there. But we're just starting to look into that.
All right, we have one over here. Ashish?
That was a great talk.
Oh, thank you.
One thing that I was curious about was, so you talked about anomaly detection from known code, right? But how far can you go? So what is the extent of inference that you can, what can you infer from the system, such as from an adversarial perspective?
Yes.
Can you go as far as, hey, can I guess encryption keys? And as the second part of this question is, if you can, what kind of machine learning backend do you need to actually get to that point?
Great question. So, yeah, there is. I'll explain this. So I'm not an expert on the anomaly detection. So there's some other members of the team that have been working on that piece. But as far as I understand it, it's window based. So we're trying to detect changes over some window of time. So if you make that window super large, very small changes in the code, you're not going to see it. If you make it too small, you're going to have a lot of false positives. That's one aspect. The ultimate goal of a program like this would be that you are able to do instruction level tracking of the processor. We're way far away from that. We're able to see certain blocks of code. And so, if an attacker was able to, insert one instruction that threw everything off, no, you wouldn't be able to detect that. So it's all in that trade-off space.
And are you sort of, is there any machine learning aspect of that where you could change the algorithm to get closer, or is it purely sort of radio related in terms of limitations?
Right. So the work I've done on this has been mostly on the radio side. Okay. So I can't really speak to the machine learning in too much detail.
Okay.
But it's a good question though.
Thank you.
All right, last question here in the back.
Yeah, nice talk. I was just wondering about the setup that you have with the antenna array and the device. Do you put this inside a Faraday cage to prevent stray radiation?
Good question. So we have not put it inside a Faraday cage. So the array, we just have it sitting in our lab. It's a very noisy lab. We're on the top floor of our building. We get all the radio stations, everything coming in. And so, part of the goal of the array processing is to be able to nullify all those environmental interferers. So we can see that. It's not in a very controlled way right now, but we have plans to do. We have a shield tent. We're going to move it into that shield tent so that we can do more controlled interference mitigation and prove that out.
Cool, thanks.
Yep.
All right, do you need another minute, Derek? All right, all set? Okay, great. Let's thank our speaker. Sorry.
All right.